Hello friends, this is Kapil Rathi. I am here to quickly review what we have done in previous session. We defined motion as change of position with respect to time. I hope you guys have noticed the spotlight I have on word position. Because if the position isn't changing with time, object isn't in motion. That is, it is said to be at rest, or also known as stationary or static. In 11th physics, from chapter 3 to 10, we are studying mechanics, the branch of physics which deals in study of motion. Now, mechanics is further divided into two branches, kinematics and dynamics. From chapter 3 to 4, in kinematics, we describe motion using the terms like position, distance, displacement, speed, velocity, and acceleration. Whereas from chapter 5 to 10 in dynamics, we explore the cause of motion. So you can clearly see in chapter 3 and 4, the kinematical part, we are going to be more mathematical, whereas in chapter 5 to 10, there would be a lot of conceptual working as well as mathematical working. Focus on describing one-dimensional motion. To describe one-dimensional motion, we must know how to position an object. To get a better grip of it, let's move to types of position. When observer starts an observation, we take time scale value to be 0. We call it initial time. It is denoted by Ti or T1. Position of an object at T1 is called as initial position. It is denoted by Xi or X1. When the observer ends its observation, time scale value is called as final time. It is denoted by Tf or T2. Position of the object at such time is known as X final or X2, known as final position. Now, between time T1 to T2 time interval has been passed on, which is denoted by delta t, which is equal to T final minus T initial. Change in position of the object during the interval of time delta t is denoted by delta x, which is equal to X final minus X initial. Note that the delta sign here means change in. It is not a number multiplied. So don't apply algebraic operation like division. Don't cancel them out. Delta in front of any physical quantity represent the change in its value. For example, delta T temperature would be final temperature minus initial temperature. So to sum up, X1 or Xi denote initial position, X2 and Xf denote final position, and delta X represents change in position. But if X is subscripted with a small t in bracket, that would denote position at a specific time t. So if I take time t equal to 5 and subscript it under x, I mean to say it is the position of object at 5th second. So x at t represents instantaneous position. So let's continue to describe one-dimensional motion. Having known xi is initial position, xf is final position, one can easily calculate the change in position delta x, which is x final minus x initial. But delta x is further measured in two possible ways. You can measure delta x by measuring the length of path from initial position to final position. That's what we call distance, a scalar quantity. This tells us delta x by measuring the length of path. But there is another version of delta x via a vector quantity displacement, where we measure the shortest length between initial position and final position. We also attach a direction from initial position to final position. Now there are lots of similarity between distance and displacement. Both are fundamentally length, so they will have same dimension capital L. They both will have same SI unit meter, and they both will be represented by same symbol delta x. But tell you they are describing the motion very differently. For example, when xi coincides with xf, When initial position and final position are same, displacement will be 0, but distance will not be. So I can say that they are not describing the same situation. Similarly, distance and displacement will be same in value only and only if object is moving in straight line along the same direction. In all the other cases, distance would be greater than displacement. So the next parameter needed for describing the motion is rate of change in position. The phrase rate means measuring any quantity per unit time. So rate of change in position is nothing but change in position per unit time, that is delta x by delta t. As delta x can be measured in two different ways, delta x by delta t, that is rate of change in position, will also be measured in two possible ways. If delta x is the scalar quantity distance, then delta x by delta t will be scalar quantity speed, which we already know as distance per unit time. But if delta x is a vector quantity displacement, then delta x by delta t would be vector quantity velocity. Now the direction of the velocity is always along initial position to final position, just like displacement. As the distance value doesn't always agree with the displacement value except for the motion in same direction along the straight line, speed and velocity values behave the same for the given interval of time. They do not coincide. Both speed and velocity are denoted by v, their SI unit are meter per second and dimensions are L t raised to minus 1. Last quantity we need to describe the motion is acceleration. It is defined as rate of change in velocity, that is delta v by delta t. Its SI unit would be meter per second square, acceleration dimension would be L t raised to minus 2 and it is denoted by symbol A. Please remember, direction of A is not obtained by direction of velocity. So there are two questions as homework. What are the two frames of reference based on frame of reference definition, and also try to find what is the direction of acceleration. Thank you everyone.